Swayam Prabha. Digital India. Educated India.
Hello students, welcome back. This is Professor Ravin Zugade from Department of Chemistry, Rashtrasanta Tukdoji Maharaj, Nagpur University. Now in this module, we are discussing about chemical bonding. This is in accordance with BSc Semester 1 syllabus of BSc Honours Chemistry course. This is the 7th lecture based on chemical bonding. In the previous lectures, we have discussed various types of bonding, including the ionic bonding and covalent bonding, the theories of covalent bonding, including valence bond theory, molecular orbital theory, and VSEPR theory. Today in this lecture, we will go ahead with various other types of bondings. This lecture has been prepared under the academic expertise of Professor L.J. Paliwal. The outline of this particular module is ionic bonding, this we have already discussed, covalent bonding, the theories of covalent bonding, the metallic bonding, and weak chemical forces. In today's lecture, we will be discussing about metallic bonding and weak chemical forces present between the molecules in liquid state. What are the distinguishing properties of a metal? When we say metal, it's a special type of an element or special type of elements which are having certain important properties. As soon as we say metal, certain properties definitely strike our minds, and those properties are: they are exceptionally good conductors of heat as well as electricity. As we try to pass electric current through the metals, or if we heat one end of the metal, the second end of the metal undergoes heating. So this is called as good conductor of heat as well as electricity. So most of the metals are known for very good conductors of heat and electricity. Secondly, mostly the metals have a tendency to show characteristic luster. Luster is a shining property. The surface of the metal is generally highly shining. You can imagine the situation like the metals like gold, silver, copper, they have got characteristic color which is having very good shining of its own. Thirdly, we can mold the metals in the form of sheets or wires, and this property is called as malleability and ductility. So the property of metals to be get molded up in the form of sheets is called as malleability, and the property of the metals to be obtained in the form of wires, that is called as a ductility. So metals are malleable as well as ductile. Fourthly, they have got very high tensile strength. If we stretch them or if we apply pressure on them, they sustain the pressure without getting broken up in the form of, say, brittle type of materials like salts. So they are having very high tensile strength, and their crystal structures are always close packed. The atoms are close packed manner, or they are arranged in a close packed manner. They have a tendency to form alloys very readily. So we will find large number of alloys like brass, bronze, etc. are formed by these metals, and these alloys have got slightly improved properties in terms of their strength, in terms of their durability, etc. as compared to the native or pure metals. All these properties are a combination of what we call as the metallic properties, and these metallic properties are the characteristic of most of the metals. Now, any theory which tries to explain the metal structure or structures of the metals or bonding in the metals should explain all of these properties which are observable properties of metals. We will discuss various theories which try to explain the metallic bonding in terms of various aspects, and many of them have successfully explained all of these properties. Let us start with first theory among them. Now, whenever we want to discuss about metallic bonding, the first question comes in my mind is, what is the type of force of attraction which binds all the metal atoms together in the metallic crystal? Now, can the metallic bond be ionic in nature? Now, in order to form an ionic bond, there is a necessity that there has to be an electron transfer from one atom to other atom. Thereby, formation of one cation and one anion should take place. So, if one atom donates an electron to another atom, a cation is formed on one side, anion is formed on another side. And there is an electrostatic force of attraction between them, and that is called as an ionic bond. Now, is such type of bonding possible in metals? Of course not, because both of them are the same atom, and hence why this atom should donate an electron to another atom. Now, in order to form such type of bond, there has to be an electronegativity difference between the two atoms. If one of the atom is more electronegative and second atom is less electronegative, then such type of electron shift is possible. Hence, this type of bonding is not possible at all in case of metals. It means that metallic bond is definitely not the ionic or electrostatic bond. Secondly, can the metallic bond be covalent in nature? Now, how many covalent bonds can be formed by an atom? The number of covalent bonds formed by any atom is equal to number of unpaired electrons present in that atom. But in case of metallic crystal, each atom is surrounded by a large number of other metal atoms, and hence the number of bonds which are formed between or by a particular atom are more than 6, or in most of the cases it is of the order of 8 to 12. Now, is it possible for any atom to form that many covalent bonds? Definitely not. It means that the metallic bond is definitely not a covalent bond. So, metallic bond is neither ionic bond nor a covalent bond. The formation of coordinate bond is not possible at all, since single electron transfer is not possible as in case of ionic bonding. 2 electron donation is not possible in case of a coordinate bonding also. So, it is entirely different type of bond, and what is that bond is the force of attraction which holds the number of atoms together in a metallic crystal. That is called as a special type of bond called as a metallic bond. The first theory which explains this metallic type of bonding is the electron C model or free electron theory. The metals, according to this theory, the metals have very low ionization potential, and so they have a very strong tendency to lose electrons. We know what is ionization potential or ionization enthalpy. It is the minimum amount of energy that is required to remove the most loosely bound outermost electron from an isolated gaseous atom. So these metals have low ionization potential or ionization enthalpy, and so they have a tendency to lose the valence electrons very easily. Secondly, the metal atoms are so close packed that their outer vacant orbitals virtually overlap on each other, and when these orbitals overlap on each other, it leads to formation of a continuity in the orbitals, and hence the metal atoms lose electrons and get converted into cations, while the outer orbitals which are overlapping on each other, the electrons are free to move anywhere among these overlapped orbitals in the form of a cloud of electrons, and that is called as the delocalized type of electrons. So the electrons are free to move anywhere in the crystal. That is, the cations are localized at their places and they are called as kernels. So we have, according to free electron theory, the electrons are free, while the cations which are formed by loss of electrons, they are stationary. Hence, the metal can be considered as sea of electrons in which cations are regularly arranged in a fixed position. Hence, the force of attraction between stationary cations and delocalized electrons is called as a metallic bond in the metal lattice. So this is actually the structure what we call as a electron C model or free electron model. Now, each of the metal atom has lost its electrons to the entire crystal, and the positively charged ions which are remaining there, they are located at fixed locations and they are called as the kernels. These kernels are localized, electrons are free, and there is a force of attraction between each cation and each electron. It is not restricted that one cation should attract only a fixed number of electrons or only a single electron, but every cation is attracted by each electron and each electron is attracted by every cation, and so there is a strong force of attraction, and this force is a non-directional electrostatic force of attraction between large number of cations and large number of electrons, and this is called as a metallic bond according to the free electron theory. Now let us try to explain all the properties which are shown by metal and what we call as the metallic properties on the basis of this free electron theory. The first property is the metallic luster. Now why the metal is shining, or why the surface of the metal is generally or it appears shining? The reason is there are large number of free electrons in the ground state of the metal, and since these electrons are free electrons, they can move anywhere in the crystal lattice in the ground state. Now when light radiation falls on this, because of the absorption of the quanta of light or quantum of the radiation, the electron gets excited to higher energy level. So that is called as the excitation of electron. So electronic excitation takes place by the absorption of radiation in the visible region of the spectrum. While this excited state is unstable and the electron reverts back to ground state, but while coming back to ground state, it emits its characteristic radiation. The phenomena of absorption of light and emission of light continues, and that goes on continuously because of falling of light on the metal surface, and as a result the metal has a tendency to show a characteristic luster. Now since the energy gap between the ground state and excited state is fixed, the wavelength of the light which is emitted by this electron will be fixed, and since the wavelength is fixed or the frequency is fixed or the energy is fixed, as a result the color is fixed. That's why we can see that the gold is yellow in color, then our silver has a tendency to, or silver metal has a tendency to show bright white type of shining, while copper is reddish in color. So every metal has got fixed energy gap between the ground state and excited state, and so every metal will show its own characteristic color. Second property of this is the thermal conductivity. Now, what is meant by thermal conductivity? If we heat one end of a metal surface, then the heat gets transferred to another end. That is called as the thermal conductivity. Now we know that according to free electron theory, there are a large number of free electrons which are present in the metal crystal, while there are fixed positively charged ions called as kernels. Now when one end of this metal is heated, it leads to increase in the temperature, which leads to increase in the kinetic energy of the free electrons as well as the kinetic energy of the fixed cations or the kernels. But kernels cannot move from their positions, so they start vibrating at their position. At the same time, the electrons start moving freely from one end to other. Now when the electron moves from one end to other, it collides with the other electrons, and also it collides with a large number of cations, and due to the collisions the energy is transferred from one end to other end. So kinetic energy of this end particle goes on increasing and it is getting transferred to the other end, and since the kinetic energy of the second end also goes on increasing, the thermal or the heat, it is getting conducted from one end to other end. So that is the reason for thermal conductivity. Third is the electrical conductivity. When we apply EMF between two terminals, the positive terminal of this supply attracts electrons from the metal, and since the metal is having large number of free electrons according to free electron theory, these free electrons get attracted towards the positive terminal. At the same time, the negative terminal of the source supply equal number of electrons to the metal, and because of the movement of these electrons through the circuit, the electrical circuit is completed, and as a result the metal has a tendency to show electrical conductivity. Fourth property is malleability and ductility. Now if we have a metal crystal, the situation is something like this. All the positively charged ions are present in localized position and there are free electrons moving over their surface. Now if we hammer this material from one side, the atoms get shifted to next position and they get rearranged in the new location, and they get attracted by the electrons which are moving over their surface, and the new atoms or new position leads to formation of the change in the structure of the surface, and hence the material becomes malleable and ductile. It does not break down easily because of the rearrangement of the ions or the kernels from the original positions to new positions, and this is possible only because of the non-directional nature of the charge or the force of attraction between the positive kernels and the negative electrons which are moving as a cloud over their surface. This is how the free electron theory or electron C theory can explain all the properties of the metals. Coming to another theory, which is a valence bond theory explained by Pauling and Slater. Now this theory was basically put forward by Pauling and Slater to explain the covalent type of bonding. According to valence bond theory, the metallic bond is essentially a covalent bond. But the problem of covalent bond, what we have discussed previously, is that any element can form only those many number of covalent bonds equal to number of unpaired electrons present in it. But according to valence bond theory, the metallic bond is essentially covalent bond, but it is not possible to form large number of bonds by a single atom. But because of resonance phenomena, we get different resonating structures, and due to resonance, a large number of atoms are bound together to form a metallic crystal. The resultant structure is a resonance hybrid of all possible structures according to theory of resonance. The most stable structure contributes maximum to the resonance hybrid. Let us take an example of lithium metal. Now we know that lithium has only one electron in the valence shell. So each lithium atom can form only one bond with another lithium atom to satisfy its valency. Now if this Li2 molecule is formed, it further cannot form more bonds. But according to valence bond theory of metals, if these two lithium atoms are bonded like this and these two lithium atoms are bonded like this, the bonds are not stationary but they are moving. So this lithium metal can be considered as a hybrid of a large number of structures, where for some time or at some instance these two atoms are linked together and these two atoms are linked together. At another instance these two are linked together and these two are linked together, whereas there is no bond between these two and these two. Simultaneously or similarly, we can have a large number of resonating structures where one of the lithium atom is getting negative charge while the other atom is getting positive charge. Now we can see that there are these two structures are equivalent structures and stable structures, so they contribute more to the resonance hybrid, while these four structures which are having charge separation like negative and positive charges, so their contribution to the resonating resonance hybrid will be minimum. So there will be these four structures will contribute less, while these two structures will contribute more to the resonance hybrid. But because of such type of resonance phenomena, all the lithium atoms are bonded together or they will remain together in the form of a metallic bond. This is what is valence bond theory suggests. Coming to the third theory of metallic bonding, that is the molecular orbital theory, or generally called as a band theory of solids. Now, according to band theory, it is based on the concept of formation of molecular orbitals from the atomic orbitals. Now, according to Mulliken's molecular orbital theory, we have seen or we have discussed previously that the atomic orbitals combine to form molecular orbitals, the bonding and anti-bonding molecular orbitals. Similar type of bonding and anti-bonding molecular orbitals are formed by various atomic orbitals by mixing of the atomic orbitals using LCAO approximation. The metallic atoms are so closely spaced that their atomic orbitals mix to form molecular orbitals. And since there are a large number of atoms, large number of molecular orbitals are formed with only slight separation of energies. And since the energy separation is very small, it leads to formation of almost continuum of energy or continuous energy situation called as a band. So band is a continuous energy pattern obtained by mixing of various atomic orbitals to form molecular orbitals. Now these orbitals are occupied by available valence shell electrons of all the atoms which are present in the metal. Some of the bands are empty, some are partially filled, and some are completely filled with electrons. Consider, due to continuous band structure, the electrons are free to move anywhere in the band, and as a result they do not remain localized. So it is similar to, or it can be considered as an extension of our free electron theory. Only difference is that in molecular orbital theory, the electrons are free to move anywhere in the band. Now consider the atom of lithium. Now lithium is having electronic configuration 1s2, 2s1. So there is only one electron in the valence shell, and valence shell is the second shell. Now if a molecule Li2 is formed, now in case of Li2, the 2s electron of one atom and 2s electron of other atom, these two orbitals will mix and it will form sigma and sigma star, the bonding and anti-bonding molecular orbitals. Since there are two electrons available, both of them will go to the bonding molecular orbital, that is sigma molecular orbital. But if there are four lithium atoms combining together, they will lead to formation of four molecular orbitals, two sigma orbitals and two sigma star orbitals. Since there are four electrons, they will be filled in the sigma orbitals, while sigma star, that is the anti-bonding molecular orbitals, will remain vacant. Now if we extrapolate such type of mixing of atomic orbitals leading to formation of molecular orbitals to large number of atoms, so in case of metal, what happens? There are large number of lithium atoms and they lead to mixing of their atomic orbitals, forming large number of molecular orbitals. And in those molecular orbitals, half of them will be completely filled while half of them will be empty. And since there are large number of molecular orbitals with very closely spaced energies, they lead to formation of band. And this band is a continuous energy and electrons are free to move anywhere in this band according to band theory or molecular orbital theory. Now this band theory is the best theory to explain the properties of conductors, insulators and semiconductors. According to this band theory, the highest energy band containing some electrons is called as a valence band, while the lowest energy band containing no electrons, that is called as a conduction band. So these two bands are extremely important. One is the highest occupied band and second is the lowest unoccupied band. So both of them play extremely important role in deciding the substance as a conductor, insulator or semiconductor. Now in case of conductors, the band is either the partially filled valence band or the valence band overlapping with the conduction band. In both the cases, we can see that if the valence band is partially filled like this, then electrons are free to move anywhere. And because of movement of electrons within a band, the substance acts as a conductor. While there is second situation where the valence band is completely filled and conduction band is empty, but they are overlapping on each other. And because of such overlap, there is a possibility of electrons moving freely among them, and as a result the substance behaves as a conductor. In general, we can say that if there is a scope for the electrons to move within a band or between two bands, then definitely the substance will act as a conductor. In case of insulator, the valence band is completely filled, the conduction band is completely empty, and there is a large separation between the valence band and conduction band. As a result, the electrons cannot move from valence band to conduction band, thereby it acts as an insulator. But in case of semiconductors, the valence band is completely filled, conduction band is empty, but the energy gap between these two is extremely small. And so, when we supply small amount of thermal energy, electrons can jump from valence band to conduction band just by absorbing the thermal energy, and thereby it can conduct the electricity in this band because of the free movement. The energy of there is an important concept of Fermi energy, which is the maximum energy which an electron can have at ground state at any temperature in the valence band. So this is Fermi energy. So this is how the metal, semiconductor and insulator, they can be discriminated on the basis of energy gap between the valence band and the conduction band. Now let us discuss various types of defects in solids. When we say solids, we will be discussing about the non-ionic solids like the metals, as well as ionic solids like the ionic compounds or ionic crystals. Any departure from the perfectly ordered arrangement of the constituent particles, that is the ions or the atoms in a crystal, they are called as defects or also called as imperfections. Now these defects in crystals can be classified into four types: point defects, line defects, surface defects or sometimes also called as the plane defects, and volume defects. As the words are indicating, point defect is a single point, non-dimensional. Line defects are one-dimensional. Surface defects or plane defects, they are two-dimensional, and volume defects are three-dimensional. We are going to discuss about all of them one by one. Starting with the point defects. We can further classify these point defects into three types: the stoichiometric defects, non-stoichiometric defects, and impurity defects. The stoichiometric defects can be further classified as Schottky defects, Frankel defect, vacancy defect, and interstitial defect, while the non-stoichiometric defects can be classified as metal excess defect and metal deficiency defect, while the impurity defects have no classification as such because it will be applicable to all the impurities. Okay, let us start with one by one. So we'll start with the stoichiometric defects. Now this type of defect is also called as an intrinsic defect or thermodynamic defect. In stoichiometric defects, the proportion of element in the solid is not disturbed. So whatever is the proportion, that remains same, and as a result it is called as a stoichiometric defect because the stoichiometry of the substance is not changed. This defect arises when there is some vacancy in the crystal lattice or when some constituent particle moves from their original sites and occupy interstitial site. The stoichiometric defects have been observed in both non-ionic as well as ionic solids. Let us see how stoichiometric defects occur in non-ionic solids, like in case of metals. Metals are non-ionic solids. So in that case, there are two types of defects, stoichiometric defects are observed in non-ionic solids. The first is a vacancy defect, where all the atoms are present at their respective locations, while some of the locations the atoms are completely missing from their positions. Such defects are called as vacancy defects. Now in this case, the atom is missing from this position. So such positions, atoms are missing at particular points, and so this comes under the point defect. Now in case of this vacancy at some lattice points, and due to abrupt heating of crystal, this type of vacancy defects are created. And due to vacancy defect, since the atoms are not present at this location, at the same time the volume remains same, the mass has reduced. As a result, the density of the metal will decrease if the number of vacancy defects go on increasing. Coming to another defect, that is an interstitial defect. Now in that case, this is possible when there are large interstitial spaces available for the atoms to migrate. So if extra atom is present in the interstitial species or extra atom is present in interstitial positions, then such defect is called as an interstitial defect. Now in such case, additional particle is present at the interstitial site and no vacancy at the normal positions. This leads to increase in the density because in the same volume now more number of atoms have been accommodated. Both of them come under stoichiometric defects because they do not affect the stoichiometry as it is a non-ionic solid. Coming to stoichiometric defects in ionic solids. Now in case of ionic solids, we find two types of stoichiometric defects. One is called as a Schottky defect and second is a Frankel defect. Now in case of Schottky defect, there is equal number of cations and anions missing from their positions, and as a result the density of the material decreases because of the vacancies at certain locations. While in case of Frankel defect, there is a shifting of ions from its normal position to the interstitial position. Now the mass remains same, volume remains same, and so there is no change in density. This type of defects are possible when one of the ions is getting shifted from its normal position to interstitial position, and normally the ions which are having smaller size, which are generally the cations, they get shifted from their original position to the interstitial positions. Now come to the non-stoichiometric defects. Now these are of two types. First of them will be metal excess defect and second are the metal deficiency defects. Now metal excess defects can be observed by two phenomena. In first case, it is possible that anion is missing from its position and the position is occupied by a free electron. So there is excess of a metal as compared to anion or its counter ion. So in the given volume or in the given crystal lattice, number of metal atoms which are positively charged, this is A positive is representing a metal. So number of metal atoms are more as compared to the corresponding anions, and the electrical neutrality is maintained by one electron occupying the position of anion. So this comes under metal excess defect. One more possibility is that the extra metal atom is occupying an interstitial position and at the same time an electron is also occupying an interstitial position to maintain the electrical neutrality. So electrical neutrality is maintained but the stoichiometry is disturbed. So if we count the number of metal atoms to number of non-metal atoms which are supposed to be or which should be 1:1, but the proportion or the stoichiometry is changed in both the cases. Both of them contain excess number of metal atoms as compared to the non-metal anionic parts. Coming to the second component, that is the metal deficiency defect. Now in that case, some of the metal is missing from the position and the electrical neutrality is maintained by another metal. The metal is same but with a different oxidation state. For example, this type of defects are very common when we are having copper atoms. Now copper has a tendency to show two different oxidation states, Cu positive and Cu2 positive. One of the position of Cu positive is missing and at some place there is a Cu2 positive. So electrical neutrality is maintained by change in oxidation state while one metal atom is missing from its position. So this is called as a metal deficiency defect. In case of metal excess defect, under certain conditions the density is reduced, under certain conditions the density is increased, while in case of metal deficiency defects always the density is reduced because of less number of atoms available. One more type of point defect is an impurity defect. Now it differs from the metal excess defect in the form that one of the sides of the metal is occupied by some impurity with different valency. So in this case, this A positive and this A positive, so two A positive atoms have been substituted by one another atom having different oxidation state. This type of vacancies or this type of defects will be observed if we have strontium present along with or in NaCl crystal. Now strontium exists as Sr2 positive ion. So when one strontium ion occupies a metal crystal position, then two Na positive ions are replaced. So this is called as a impurity defect. All these types are of the point defect type. Now come to the line defects. Now line defects is one dimensional defect. Point defects are non-dimensional. Now line defects are mostly due to misalignment of the ions or presence of vacancies along a complete line, and the lines of the ions are missing in the otherwise perfect array of ions, and that is called as a edge dislocation. Line defects weaken the structure along one dimensional space, and the defect type and defect density affects the mechanical properties of the solid because the entire line is missing, so mechanical property gets affected. Consider this type of structure where the entire line has been shifted to some different location. So this is called as a line defect. It is one dimensional defect in the entire crystal lattice. Next is a plane defect, or what we call as a surface defect. It is a two-dimensional surface defects. The surface defects are along the grain boundaries, and a grain is a single crystal. If we see this, there are a large number of grains along the surface. So there are grain boundaries where the defects are observed. This is called as a plane defect. One part. Secondly, the plane defects may also arise because of the stacking imperfections or stacking faults. For example, if we consider the FCC lattice, now FCC lattice has a stacking sequence A, B, C, and so on. But if one of this is completely missing, for example, if this C layer is completely missing, now the pattern becomes AB, ABC, and so on. Now this C array is completely missing from its position. So this is called as a stacking defect. If we see this, observe this structure carefully. This is A array, this is a B array, this is C array, and then there should have been complete A array, but this array is missing over an entire line. So this is called as a line, the plane defect, with the entire two-dimensional plane is missing from its position. The volume defect, it is a three-dimensional defect observed in crystals, and it is formed during the crystal growth. It is because of various voids, cracks, grooves or pits which are developed inside the crystal lattice when the crystal lattice grows in size, and this leads to three-dimensional volume defect. If we see this crystal structure, there are large number of atoms, but there is a volume cavity along all the three dimensions. So such cavity is produced or getting trapped within the crystal structure. This is called as a volume defect. Now after the discussion of various defects in solids, we will discuss about the intermolecular forces in liquids. Now the difference between the solid state, liquid state and gaseous state is only the interparticle distance. In case of solid state, the particles are close packed. In case of liquid state, they are a bit away from each other or apart from each other, while in gaseous state, they are maximum distance away from each other. So it is only the interparticle difference or intermolecular distance makes the substance solid, liquid or gas. When you heat a solid, the interparticle distance increases and it gets converted into liquid at its melting point. When we further heat this liquid, the interparticle distance further increases, converting it to gaseous state at its boiling point. So there is a fundamental difference between these three states of matter. Among them, liquid state is an intermediate state, where in case of solid there are strong interparticle or intermolecular or interatomic forces, and these forces are long range forces. In case of liquid, such forces exist but they are short range forces, while in gaseous state the forces are negligible, and according to kinetic theory of gases postulate, there are no forces existing between the gaseous molecules for the ideal gas. In real gases there are small forces, but liquid state is an intermediate state, and so there are short range forces between the molecules, and we will discuss them one by one. Such forces are the dipole-dipole forces, the ion dipole forces, the dipole-induced dipole forces, London forces, and the hydrogen bonding. We will discuss all of them one by one, starting with the dipole-dipole forces or dipole-dipole interaction. Now, what is meant by a dipole? Now, some molecules are neutral as such, but they involve charge separation. And whenever there is a charge separation, there is the center of positive charge away from the center of negative charge. And in that case, we say that a permanent dipole is formed, or there is a separation of charges leading to formation of two poles called as dipole. And the opposite ends of the different dipoles, they attract each other. For example, if we try to represent diagrammatically, if this is one dipole having a permanent positive charge shifting at one terminal and negative charge shifted at other terminal, then there will be a force of attraction between the negative terminal of one dipole to the positive terminal of another dipole. So such a type of forces are called as the dipole-dipole forces. Now these forces can exist in this particular fashion, or two dipoles, they are adjacent to each other, facing or with their opposite charges close to each other, or there can be perpendicular type of interaction like this. So all these types of interactions are possible between the permanent dipoles within a liquid, and such forces definitely arise whenever the liquid is a polar liquid, or the molecule or liquid molecules are polar in nature. For example, in case of water molecules or NH3 molecule, where there is a permanent dipole formations. Second type of forces are the ion dipole forces. Now, some liquids, they have a tendency to undergo self-ionization. For example, we know that even water has a tendency to undergo self-ionization, liquid to formation leading to formation of H3O positive and OH negative ions. And these ions are present at very low concentration. Even under neutral pH conditions, we know that 10 raised to minus 4 molar, 10 raised to minus 7 molar concentration of H plus, that is H3O positive, and 10 raised to minus 7 molar concentration of OH negative exist at around 18 degrees Celsius temperature or at room temperature. So such ions exist in the liquid even at room temperature without any additional or even without any external agent. Now such ion is attracted towards the opposite end of the solvent dipole. So because water itself is a dipole or a polar molecule and it contains ions of its own, so there is a force of attraction between the ion and the dipole, and this force will be very strong if the solvent is highly polar. So we can show this type of interactions as negatively charged ion will be attracted by the dipoles with the positive terminals facing the ion. Similarly, the positively charged ion or the cation will be attracted by the dipoles with their negative terminal facing the cation. So this type of interactions will be definitely existing in various liquids, including even the water. Third type of interaction is a dipole-induced dipole interaction. Now this is dipole-induced dipole is an interaction between a permanent dipole and an induced dipole. Now some molecules are not polar but undergo polarization when come in contact with a permanent dipole, and such dipole is called as a induced dipole, which is a temporary dipole formation, and the force of attraction between a permanent dipole and induced dipole will be called as a dipole-induced dipole interaction. For example, if we consider a non-polar molecule like this, having no charge separation, because the center of positive charge and center of the negative charge, they are coinciding with each other. Therefore, it is definitely not a polar species. But when it comes in contact with a dipole, which is a permanent dipole, then the positive terminal of this dipole attracts the electron cloud on this molecule, whereas at the same time this positive terminal repels the nucleus of this molecule, thereby causing a polarization in this molecule. So the non-polar molecule is now becomes polar, because now the negative charge center has been shifted to somewhere over here, whereas the positive charge center is shifted backward and in this direction. As a result, this species formed is now called as a induced dipole. Now it is a temporary dipole because this type of interaction will be there, or this type of situation or structure will be there only if this dipole is present. As soon as this dipole is removed, this structure will come back to its original structure like this. So this type of structure is a temporary structure called as a induced dipole. Now the negative charge cloud of this induced dipole getting attracted towards the positive terminal of a permanent dipole, and such interaction or such force is called as a dipole induced dipole interaction. One more type of force called as the London forces. Now these forces are the weakest forces among all. Since electrons are continuously revolving, at some instance there is unequal charge distribution leading to formation of instantaneous dipole. So now the species is not polar and it is not under influence of anything or any outside body, but itself it undergoing instantaneous dipole formation due to unequal charge distribution due to revolving electrons. And when such instantaneous dipole comes in contact with non-polar molecule, it induces polarization into it, leading to formation of an induced dipole. Now one is an instantaneous dipole, second is an induced dipole, and a force of attraction between one induced dipole and second instantaneous dipole, that is called as a London force. For example, if you have an instantaneous dipole formed due to revolving of electron, at some moment there is more electron cloud in one particular direction. This leads to instantaneous dipole formation. When such instantaneous dipole comes in contact with a neutral non-polar molecule, it induces dipole moment into it by attractive forces, and now there is an attractive force between instantaneous dipole and induced dipole, leading to formation of London forces. They are temporary forces and they are very short range forces, because the London energy is inversely proportional to r raised to power 6. As normally the force of attraction between any two charged species is directly proportional to 1 upon r square, or we can say that it is inversely proportional to square of the distance under normal conditions. But London forces are the forces which vary inversely as 6th power of the distance between the two forces. So they are very short range forces. One more force of attraction that exists between the solvent molecule in special cases called as hydrogen bonding. Now when hydrogen atom is covalently bonded to small strongly electronegative atom, the bonded electron pair is pulled by the other atom and highly polar molecule is formed, and there is a sufficient positive charge on the hydrogen end of the molecule that attracts from the hydrogen bond with the nearby electronegative atom of the adjacent molecule, and the strongest bonds are formed between the hydrogen whenever it is bonded with highly electronegative atoms like fluorine, nitrogen, oxygen, etc., like HF, NH3, H2O, etc. They have a tendency to show very strong hydrogen bonding. We will see what are the types of hydrogen bonding. The first type of hydrogen bonding is a intermolecular hydrogen bonding. Now as the word is indicating, it is existing between two molecules of the same species. For example, if we consider HF. Now HF is having fluorine which is more electronegative than hydrogen. So electron pair gets shifted towards fluorine atom. As a result, fluorine atom is getting partial negative charge. Hydrogen is having partial positive charge. So fluorine atom of one molecule attracts the hydrogen atom of other molecule. Through this, the hydrogen bonding is existing between two different molecules of the same species. Such type of bonding will be called as a intermolecular hydrogen bonding, and such type of intermolecular hydrogen bonding exists in HF. Similarly, in case of H2O also, we know that oxygen is more electronegative, so oxygen bears partial negative charge while the hydrogen atoms bear partial positive charges. So hydrogen of one molecule attract the oxygen of the other molecule, thereby intermolecular hydrogen bonding exists in water. Similarly, in case of NH3 or even in case of the alcohol molecules, we can see ROH, there is a strong intermolecular hydrogen bonding. Second type of hydrogen bonding is a intramolecular hydrogen bonding. When we have hydrogen atom and a electronegative atom, both of them exist in the same molecule. For example, this is salicylaldehyde molecule. We have OH group on one side and we have a CHO group on the other side. The oxygen atom of CHO group attracts the hydrogen atom of this OH group, thereby leading to formation of hydrogen bond between them. Similarly, this is a molecule which is a orthonitrophenol. So we have a nitro group on the ortho position of OH group in phenol. So we have this hydrogen getting attracted towards the oxygen atom of this nitro group. So this is a intramolecular type of hydrogen bonding. So we have intermolecular as well as intramolecular hydrogen bonding. This hydrogen bonding affects various properties of molecules, and three important consequences of this hydrogen bonding, or three important effects of hydrogen bonding on the properties of the molecules we will be discussing. The first property is melting and boiling points of various compounds. Now we know that compounds having intermolecular hydrogen bonding will have high melting and boiling point. Now what is melting point? It is a temperature at which our solid gets converted to liquid. Our boiling point is the temperature at which liquid gets converted into gas. Basically, when a solid gets converted to liquid or a liquid gets converted into gas, the intermolecular distance increases. Now if there is an intermolecular hydrogen bonding, then more energy will be required to separate the molecules from each other, and as a result the melting or boiling point will increase. This is quite obvious because since the molecules are associated with each other, more energy is required for their separation, and hence the hydrides of fluorine, oxygen, nitrogen, etc. have higher melting and boiling points as compared to their analogues of their own group. We will see diagrammatically what is the effect of this hydrogen bonding on various molecules. This diagram is a clear-cut indication. If we see this CH4, SiH4, GeH4 and SnH4. Now there is no hydrogen bonding because the electronegativity of carbon and hydrogen, they are comparable, and as a result there is no hydrogen bonding in CH4, SiH4, GeH4 and SnH4. So quite obviously, with increase in molecular weight, the boiling point goes on increasing continuously from CH4, SiH4 to GeH4 to SnH4. But when we compare the same thing with NH3, PH3, ASH3 and SbH3, we can see that PH3, AS3 and SbH3, there is a continuous increase in the boiling points, but in case of NH3, it has got exceptionally high boiling point as compared to this, whereas the expected boiling point should have been somewhere over here. The shift or increase in the boiling point of ammonia is because of very strong hydrogen bonding, which is an intermolecular hydrogen bonding in NH3 molecule. This is because nitrogen is much more electronegative as compared to hydrogen, leading to very strong hydrogen bonding between the ammonia molecules. Similarly, we have HF, which is a very strong hydrogen bond showing compound, has got much higher boiling point as compared to HCl, HBr and HI. Similarly, water is having very high boiling point as compared to H2S, H2Ac and H2Te. Now if we compare this H2O, H2S, H2Ac and H2Te, at room temperature H2S, H2Ac and H2Te, all the three exist as gases, while at room temperature water exists as liquid. So among the hydrides of this group, 16 elements which are oxygen, sulfur, selenium and tellurium, only H2O exists as liquid at room temperature, while the others exist as gases at room temperature because their boiling points are much below 0 degrees and they exist as gases at room temperature. One more consequence of hydrogen bonding is on the solubilities of various liquids. Now, compounds showing a property of hydrogen bonding are highly soluble in water because those compounds can form hydrogen bonds with water. They will have very high solubility in water. For example, alcohols are soluble in water. Ammonia is soluble in water because of strong tendency to form hydrogen bonds. Many gases even like HCl and HCl and HF, they have a tendency to dissolve in water because of strong hydrogen bond formation. More tendencies of formation of hydrogen bond with water, more is the solubility of that compound in water. For example, alcohol can form hydrogen bonds with water molecules. So, alcohol can enter into the hydrogen bonding structure of water molecule and so it can undergo dissolution in water. Alcohols very easily dissolve in water, but those compounds which cannot form hydrogen bonds with water have very low solubility. Like many organic compounds, they do not dissolve in water because they are unable to form hydrogen bonds. But alcohols definitely can form hydrogen bonds because of the electronegativity difference between oxygen and hydrogen in case of alcohols. Third important consequence is on the viscosity of various liquids. The viscosity is defined as resistance to the flow of liquid. That is called as viscosity. Now, if a compound has intermolecular hydrogen bonding, the molecules are associated with each other, and if there is a strong association between them, then the flow becomes very sluggish or the flow of the liquid gets restricted. Now, if we compare three liquids, the methanol, the glycol and glycerol, now the structures of these three can be shown like this. Methanol has one OH group, glycol has two OH groups, whereas glycerol has 3 OH groups. When we go from methanol to glycol to glycerol, as the number of OH groups go on increasing, the hydrogen bonding becomes stronger and stronger. And as the hydrogen bonding becomes stronger, the viscosity goes on increasing from methanol to glycol to glycerol. So in short, we can say that hydrogen bonding leads to increase in viscosity of the liquid because of the strongly associated structures of the molecules. This is all about in this lecture, and this is all about in this module on chemical bonding. So in chemical bonding, we have discussed about types of bonding including the ionic and covalent bonding, then various theories of covalent bonding like valence bond theory, VSEPR theory, molecular orbital theory, and we have discussed about various other aspects like defects, then the metallic bonding, and now in the end the other intermolecular forces. This is all about this module. In the next module we will be discussing about oxidation and reduction. Thank you very much.